We're continuing our discussion of the potential due to an annulus. In part A, we calculated the potential at a distance z from the origin on the z-axis, the central axis, and then we determined the electric field at all points on the z-axis by differentiating the potential, and we showed that this electric field is the same as electric field due to an infinite sheet of charge in the limit a goes to 0 and b goes to infinity. Now, part D, if A is 5 centimeters and B is 10 centimeters, and the total charge on the annulus is 1 microcoulombs, what is the potential at the origin? Okay, now the potential at the origin implies Z is equal to 0. So in my potential expression, I'm going to substitute Z is equal to 0. So let's see. Z is equal to 0 will give me a B here and an A here. So this is going to be the surface charge density sigma divided by 2 epsilon 0 B minus A. The charge density sigma is the total charge the annulus contains, Q, divided by the area, pi r square, pi b square minus pi a square, the annulus. Now, this is basically assuming I have a uniform charge distribution. The potential at z is equal to 0 will become the total charge Q divided by 2 pi epsilon 0 b square minus a square multiplied with b minus a. Now b square minus a square is b minus a times b plus a, so I will be left with a potential V at z is equal to 0 is the total charge Q divided by 2 pi epsilon 0 b plus a, because b minus a's will cancel. So this is the potential. Now, if I substitute the numbers to obtain the numerical value of the potential, V at z is equal to 0. 1 over 2 pi epsilon 0 is twice Coulomb's constant, 2k. So I have 2kq divided by b plus a. And k Coulomb's constant is 1 over 4 pi epsilon 0. This is 1 over 4 pi epsilon 0. And the potential then becomes potential at the origin, z is equal to 0, twice Coulomb's constant. So I have 2 times 9 10 to 9. And I have the charge 1 microcoulomb, 1 10 to minus 6 coulombs, divided by b plus a, that is 10 plus 5, 10 to minus 2 meters. Remember that A is 5 centimeters, B is 10 centimeters, so it is 10 to minus 2 meters. So plugging in these numbers and doing the calculation, I find that the potential at z is equal to 0 is roughly 120 kilovolts. So that's the answer to this part. And for the last part, let's see what we're after. If a particle with mass 1 grams, much less than the mass of the annulus, and charge 1 microcoulombs, is placed at the origin and given the slightest nudge. Now this is a positively charged particle, positively charged annulus, so it will feel an electric field upward, so it will start accelerating. It will be projected along the z-axis. In this case, what will be its ultimate speed? All right. So this particle initially is at the origin, so it has an initial potential energy. Its charge multiplied by the potential created by this annulus at z is equal to 0. So I have 1 times 10 to minus 6 coulombs times 120 kilovolts. So that is 0.12 joules. And initially it is at rest, it's given a slight nudge. Final kinetic energy of the particle will be 1 over 2 mv square, its final speed. And the final potential energy will be, because z will go to infinity, it's going to become 0. So what will be its final speed? The change in kinetic energy plus the change in potential energy should be equal to 0 because we only have conservative forces. So the change in kinetic energy is minus the change in potential energy. That is minus final potential energy minus the initial potential energy, 0.12 joules. So I find that my final kinetic energy is 1 over 2 mv square, which is equal to the potential energy qv at z is equal to 0. So the ultimate speed it will have, v, is going to be equal to 2q potential at the origin, z is equal to 0, divided by m square root. So this will be the ultimate speed it has at infinite distance from the center. So if I substitute the numbers here, this ultimate speed will be 2. Now I can substitute the charge, 1 10 to minus 6 coulombs, 120 kilovolts, 120 10 to 3, divided by the mass, it's 1 grams, 1 times 10 to minus 3, and all of this inside the square root, that is square root of 240, and I find that the ultimate speed it has is 15.5 meters per second. Okay, so in this part of the problem, I have used the answer from part A for the potential as a function of z, substituted z is equal to 0 to find that the potential is sigma over 2 epsilon 0 b minus a, where sigma is the total charge q divided by the total area pi b square minus a square. And for Coulomb's constant, I use 1 over 4 pi epsilon 0. I find that the potential is 2kq divided by b plus a. Substituting the given numbers, this is 120 kilovolts. If you put a particle at z is equal to 0 with charge q, it will acquire a potential energy q times v, which is 1 times 10 to minus 6 times 120 10 to 3, so 0.12 joules. And when you give it a slight nudge, what will happen is that it will feel a force. The force will be directed upward, so this particle will fly away on the z-axis if it's constrained to move on the z-axis like this. And it's going to reach a final z value of infinity, and at that point the potential energy will become 0. Initial kinetic energy is 0, final kinetic energy is 1/2 mv squared. The mechanical energy is conserved since I only have conservative forces in the problem. The system is isolated, so I have delta k is equal to minus delta u, implying that the final speed is square root 2qv over m. And substituting the numbers, we find 15.5 meters per second as the answer to part E.